Welcome to the introductory video about optical refraction. We're going to look at what happens when light or any electromagnetic wave, or in reality any wave, changes from one medium to another. We first saw this back in the Mastery Lab about waves. I think it was procedure 10, where we sent the wave from the slinky to the heavy coil brass spring. And part of that wave bounced off of the interface being the connection between the two mediums, and part of that wave went through the interface. The part that went through is called refracting. It's all in chapter 36 for when you do the reading.
No, the pencil isn't really bent, although it appears to be. And physics teacher Bruce Illingworth in the pool doesn't really have his head displaced as it appears. The explanation for these strange appearances involves changes in the speed of light. Here we see a ray of light entering a pane of glass at an angle. The speed of light in a vacuum we call c constant. It's nearly c in air, but its average speed v inside the glass is considerably less than c. We see it emerges from the glass parallel to, but somewhat displaced from its initial path. Light changing speed from one material to another gives rise to refraction. If you roll a pair of cartwheels down a slight incline from sidewalk to grass, the wheels roll slower on the grass than on the sidewalk. Why? There's more interaction of wheel surfaces with grass than with the smoother sidewalk. If you roll the wheels at an angle, so one wheel meets the grass while the other is still on the sidewalk, the wheels will swivel from their straight line path. Due to the change in speed, the direction of travel changes. Likewise with light. Here we see wavefronts of light heading toward water. Light travels slower in water than in air because there's more interaction with the denser water than with thinner air. The wavefronts in this diagram represent wave crests of light. You can see how the wavefronts swivel when they meet the water surface. They bend from their original course. We say the rays are refracted. Note that the direction a ray is moving and its wavefront are always at right angles to each other. Notice another thing. The distance between wavefronts is less in the water. Interesting. The wavelength of waves is somewhat compressed. But another thing, the frequency of the waves remains the same. Important to know.
All right, so one of the points I wanted to make sure that you got out of that part of the video was that the frequency doesn't change when you change mediums. The speed does, the average speed, and therefore the wavelength changes, but not the frequency. The frequency stays the same from one medium to another.
But what about refraction? Refraction, the way light bends at a surface. How do we measure that?
Refraction is described by two angles as measured to a perpendicular of the surfaces.
The angles of incidence and refraction are measured from the normal. Here we see the angle of refraction is less than the angle of incidence.
I want you to notice how the angle of incidence is always larger than the angle of refraction.
Or two, and look at some of the equations for this. I'm on page 4 of our equation sheet, and you can see up here in the geometric optics box, these equations along the top line we have talked about with spherical mirrors and with mirrors in general. The really important ones for refraction are these two down here. The n equals c over v and ni sine theta I equals nr sine theta r. The first one, n here, is the index of refraction. So that is a number that is guiding us to how much the average speed of the wave changes in the medium. C is the speed of the wave in a vacuum. Of course, for light, that has that value of approximately 3 × 10⁸ meters per second. But this can apply to other waves.
Just how much the speed of light differs from its speed in a vacuum is given by the index of refraction, n, of the material. N is the ratio of the speed of light in a vacuum to its speed of light in material. For example, the speed of light in a diamond is 124,000 kilometers per second. And so the index of refraction for diamond is 2.42.
This Snell's law, this longer one here with the trig in it, tells us and predicts and explains how the light changes its path, or the wave changes its path when it enters that new medium, based on the angles measured, incident angle and refracted angle, as it enters the new medium, always measured, of course, to the normal.
The quantitative law of refraction involves a bit of trigonometry and is called Snell's law, credited to Willebrord Snell, a 17th century Dutch astronomer and mathematician. It's n sub 1 sine theta sub 1 equals n sub 2 sine theta sub 2, where n sub 1 and n sub 2 are the indices of refraction of the media on either side of the surface, and theta sub 1 and theta sub 2 are the respective angles of incidence and refraction.
So this is Snell's law, and this is our index of refraction. We should also keep in mind, remember, that we have the law of reflection up here. I wanted to expand a little bit more here, bring out some details about what is happening when light changes mediums, or any wave, truly. In my simulation here, I've got a pool of water down the bottom, and I have got my normal line drawn in here, and I have a laser, a red laser, and when I turn it on, it is going to interface, hit the interface. The majority of it is going to refract, go through, but you can see that there is a reflected part here also. So at this interface, just like we saw in the Mastery Lab on waves, there's refraction and reflection. If I bring out my intensity meter, almost 95% of it is refracting, and that leaves just over 5% to reflect. If I change my angle here, notice that my angle of reflection always equals my angle of incidence, but my angle of refraction is different. And now I bring in my intensity meter, and I have almost 39% reflected and 60% refracted. If I went way up here, almost to 0 degrees, because remember I'm measuring everything to the normal, I'm only getting 2% reflected. I'm getting almost 98% refracted. So the amount that it reflects and refracts, what percentage, depends upon that angle of incidence.
Note here how refraction accounts for seeing a fish to be nearer the surface of water than it actually is. Because you're accustomed to seeing light following straight line paths, you place the fish closer to the surface. If you're spearing fish, you'll want to know about this. Note also that due to refraction, the full root beer mug appears to hold more root beer than it actually does. Sample light rays coming from the root beer refract toward the viewer's eye. The result, a fuller looking mug. When the mug is partly in water, what's happening? Aha, light from the mug through the water doesn't speed up as fast as when through air. With less refraction, we get a better view of the amount of root beer in the mug. Yum! Atmospheric refraction accounts for mirages. Light travels a bit faster in hot air than in cooler air, so if the air near the ground is warmer than the air above, as it is in desert in the daytime, light from the palm tree refracts upward, which is to say, bends upward. Your eye interprets this as a reflection, when it is really refraction. Light from a distant blue sky that refracts upward in the same way gives the illusion of water not far ahead. This is more common on roads, where air warmed at the surface produces the same effect. Whenever we look downward and see sky, it's either reflection or refraction. Sometimes the two are confused.
So we're looking now at internal reflection total internal reflection, and this is also something that we have either looked at in the lab or we're going to look at in the lab depending upon the sequence of your class.
When you send light from water internally into air, you're going to get refraction. The steeper angle you pick, the steeper it will refract, until at some specific angle, it refracts at 90 degrees. When this happens, you will get no refraction at all, only reflection. You will get total internal reflection.
Now, let's swap this up and let's change the top to water and the bottom to air. Now I still get refraction, but one thing I want you to notice as I toggle between these two, when I had the less dense up top and the more dense optically down the bottom, I'm always bending towards the normal on my refraction. The higher that amount, let's go to glass here, the more I'm bending towards the normal. When I switch those up, when I go from, say, glass up here down to air down the bottom, notice I'm bending away from the normal as I go in. So the less dense, the lower the index of refraction, the more I bend away from the normal. This is why if I go from a more dense to a less dense material, I reach a point where my angle of refraction is 90 degrees, and therefore I stop refracting. I'm just going down the interface, and all I get above that is reflection. And that angle, where my angle of refraction is 90 degrees, is called the critical angle. And above that angle, I have only reflection. This does not happen and cannot happen in the reverse situation where I'm going from air, a less optically dense medium, to glass, a more. Since I'm always refracting towards the normal, there's no way to get my angle of incidence below 90 and my angle of refraction to be above 90. So I cannot totally internal reflect from a less optically dense material to a more optically dense material.
In the same material, light of different frequencies has different speeds, different indices of refraction. Frequency plays a major role in a diamond. Here we see a sample ray of white light entering a diamond. Violet light is slowed more than red light, so refraction is greater for violet than for red. We know that the average speed of light is less than c in a transparent medium. How much less depends on the nature of the medium and on the frequency of light. The speed of light in a transparent medium depends on its frequency. Violet light travels about 1 to 2% slower in glass or water than red light. Light waves with colors between red and violet travel at their own intermediate speeds. So light refracts by different amounts according to frequency or color. We see white light encountering a glass prism. At the first surface it refracts, with blue refracting more than red. The two colors separate. When emerging, light undergoes a second refraction and the separation is further increased. This separation of light into colors arranged according to frequency is called dispersion. It's what enabled Isaac Newton to form a spectrum when he held a glass prism in sunlight. Dispersion also occurs in water, where violet light is slower than red light by about 1%. A most spectacular illustration of dispersion by water is a rainbow. For a rainbow to be seen, the sun must be shining in one part of the sky, and water drops in a cloud or in falling rain must be present in the opposite part of the sky. When we turn our backs toward the sun, we see the spectrum of colors in a bow. Seen from an airplane, near midday, the bow forms a complete circle, with the shadow of the airplane in the center. All rainbows would be completely round if the ground were not in the way. Here we see refraction and internal reflection in a sample water drop. The illustration shows only the red and violet rays. All the other colors are in between. This is one of millions of tiny spherical drops that act like prisms. Follow the ray of sunlight as it enters the drop near its top surface. Some of the light is reflected, which we don't show, and the remainder is refracted into the water. At this first refraction, violet deviates the most and red the least. Reaching the opposite side of the drop, each color is partly refracted out into the air, not shown here, and partly reflected back into the water. Arriving at the lowest surface of the drop, each color is again reflected, not shown, and refracted into the air. This second refraction is similar to that of a prism, where refraction at the second surface increases the dispersion already produced at the first surface. After two refractions and a reflection, the outgoing light can make an angle with the incoming rays of anywhere from 0 degrees to a maximum of 42 degrees, depending upon where the light strikes the droplet. Although each drop disperses a full spectrum of colors, an observer is in a position to see the concentrated light of only a single color from any one drop. Often a larger secondary bow with colors reversed can be seen arching at a greater angle around the primary bow. We won't say more about the secondary bow except to say it's formed by similar circumstances and as a result of double reflection within the raindrops. Because of this extra reflection and extra refraction loss, the secondary bow is much dimmer and its colors are reversed.
All right, so that is all of the information for optical refraction, and I'll see you in class.